So now we know how to find minimal juggling patterns. We take a nice square board and we place rooks on them so that no two rooks are in the same row or in the same column. We have to make sure we use a maximum number of rooks, in other words, exactly one rook in each row and each column. And boom, we have a minimal juggling pattern. And all minimal juggling patterns are made this way. Nice! But there's other things that we can do. You see, by changing the board, we can add restrictions to the juggling patterns. So let's do a quick example. So let's suppose we want to find all the juggling patterns of period 5 where the only throws that we can use are 1, 2, and 3. That's it. We can only make those throws. Now, how can we do it? Well, we go back and we say, look, what we're really saying is, let's think about it in terms of our rook placement, right? Because we have our board, and we say we only want throws of the form 1, 2, or 3, and that's good. There's nothing above 5. So it's really saying it's a subset of the minimal juggling patterns. So how do we go about identifying them? Well, we knock options out. We can't have any 0 throws, so we knock those out. And we can't have any 4 throws, so we knock those out as well. And now we say, great, what's left? Well, the parts that are left are places where we can put our rooks. So now it's like we're doing a rook placement, but instead of using the whole board, we're just going to use sort of a smaller subboard. But again, 1 rook in each row, 1 rook in each column. So if we can count how many ways there are to do this, then we can count how many juggling patterns there are. There actually is a nice way to do this, which we'll talk about eventually. There's still lots of time, right? But for now, let's just find some, right? Okay, so I'm going to grab some tokens. You should always, of course, keep some tokens handy with you. And we just start placing. And we see how we do. Okay, so there's a 3. There's a 1. Let's see. We could put a 3 again. And if I put a 3 there, and then what happens? Well, can't do it, right? We say, look, where's the space? It has to go right there. That's crossed out. Okay, so we can't start there. Well, all right. So maybe we don't do that. We can put a 2 there. We could put a 3 there and a 1 there. There you go. So our goal was to find juggling patterns. Here's one of them. Here we go. 3, 1, 2, 3, 1. Can we find more? Oh yeah, sure. It's easy, right? Just there. Boom. There's another one. 3, 1, 2, 2, 2. And of course, we can do all sorts of things. Some are pretty easy to spot, right? We go 3, 3, 3, 3, 3, and so forth and so on. But the moral is we can now find these. Now, this pattern, 3, 1, 2, 3, 1, it's actually kind of a fun pattern. And it's not hard to juggle. So let's talk about it for just a second. Now the pattern 3, 1 is a very easy pattern. And it's one that people can oftentimes juggle without much thought, right? So it's you throw a ball of pie with one hand and a quick pass with the other. 3, 1, 3, 1, 3, 1, 3, 1. And you can go in 2 different directions. So you can also go, whoops, too much gravity today. All right. So again, going the other direction. So we see the 3, 1 showing up. In fact, it shows up twice here. We see the 3, 1. There's another 3, 1. There's this extra 2. Well, what's that effect? Well, the effect is the following. So watch the balls. So we're going to go 3, 1, and then what? 2, and then 3, 1. Back. Okay? So, and now, what goes next? Well, now it's 3, 1, 3, 1. So what happens is so for example, I have orange and white balls. So the orange ball goes for 2 throws above, and then the white ball goes for 2 throws above. And it's not so bad. Not so bad, right? It's mostly just a matter of bookkeeping, and it can be easy to lose track. Hopefully I'm not doing that too much, but there you go. 3, 1, 2, 3, 1. Not so bad. It's always fun to try some new patterns. The more you practice, the better you get. Now, there's a nice part of mathematics called rook theory, which actually looks at the questions about placing these non-attacking rooks on boards. See, you don't have to use only things that come from these nice square boards or kind of subboards that we look at for juggling. You can look at any board and ask, okay, how many ways can you place rooks? And the other thing is, you say, look, maybe you don't have to place as many rooks as possible. That's perfectly fine. And then you can still ask the question, how many ways are there to place this many rooks on a board with this configuration? All right, and the answers can be interesting. And so we want to demonstrate this. So we're going to come up with the shape. We'll call it the end triangle for now. And it's kind of a strange name for it. The triangle is not so hard to see. The end part is a little bit more unusual because you say, well, shouldn't it be like how many squares there are here? Well, it turns out that there's, for example, n minus 1 squares there and n minus 1 squares there. But for our purposes, we want to call it n. And you'll see why as we go on in a second here. And so, how many ways are there for us to place k non-attacking rooks on the end triangle? All right, I want to answer this question because it's really cool. It's such a beautiful answer. You know, oftentimes you look back in your life and there's certain things that you remember. And I remember when I learned the answer to this, and I remember like where it happened. I remember who told this. And I was like, wow, there was my life before I knew this answer, and there's my life after I knew this answer, because it's so cool. Okay, let's not get too far ahead. Let's take a look and see if we can do some small cases and see if maybe we can get a sense of where we're going. All right, so we have this sort of triangular shaped board, and we're trying to place rooks on it. So let's get data. A great way to start looking at things is to look at data. Data is a fantastic thing. You should always ask yourself, what's the data telling me? Okay, so what's the data telling us? So let's start. So we have n equals 1. So this is the picture. Now you'll notice there's no place to put a rook. So you might say, okay, nothing can be done. Okay, be careful. Sometimes nothing is something. And by that we mean, hey, sometimes when we say that nothing happened, that's a case that we need to consider. So we need to keep track of those situations where nothing occurred. So in this case, for n equals 1, we do have the possibility, look, I can put no rooks down. That's not an issue. And I can do it in one way. And the one way is just don't do anything. All right. In fact, that's a general rule of thumb. If I want to put no rooks down, I can do it in exactly one way, which is to not put any rooks down. So we can come over here, n equals 2. All right, so we can still say that k equals 0 is still 1, but there's a square, right? So I can put one rook down, and I can do it in one way. Okay, so k equals 1 is 1. All right, not so bad. Okay, let's go to our next one. Okay, again, do nothing, always an option, one way. Okay, suppose I wanted to put one rook down. Well, the nice thing about one rook is if there's one rook, you can't have two rooks attack each other. So that means that what? Well, I can put that rook anywhere I want it. So I can put it in any one of those 3 places, which means I get 3. Okay, well, what if I want to put 2 rooks down? Well, now we have to be careful. We can't have them both be in the same row and can't have them in the same column. So there's just one way to do it, right there. Boom, boom. That's it. That's the only way to do it. Okay, so 1. All right. Well, how about the next case? Okay, well, k equals 0, still a freebie. Just one way to do that. All right, k equals 1. Well, let's see. We can do it in 1, 2, 3, 4, 5, 6. It's a number of cells. Okay, so k equals 1 is 6. How about k equals 2? All right, well, for that, okay, we'll put our second one here. So let's count. So how many ways, suppose, for example, if we put one rook there? Well, the other rook can be in any one of those 1, 2, 3 cells, right? So there's 3. We're not done yet. What if I put my rook here? Well, I can have 2 options. So there's 1, 2. Okay, so 3 plus 2, we're up to 5. What if I put a rook there? Well, not a lot of options, right? But there is this place right there. Good. Plus 1 more makes 6. Did we get them all? No, we didn't, right? There's actually 1 more, which says, hey, maybe there's no rook down here, in which case we can put it there. 1 more, 7. So there we go. There's 7 ways to do that. All right, what if I want 3 rooks? Well, here, it's tough. It's tough, right? There's not a lot of ways to do it. In fact, there's just 1 way, right here along the diagonal. Any other place, you can't get all 3 rooks there without some pair of them trying to attack each other. All right, so there we go. There's our data. We have data. All right, well, now that we have data, the next thing to do is to start thinking, okay, have we seen anything like this before? Let's look at our numbers. 1, 1, 1, 1, 3, 1, 1, 6, 7, 1. These sound familiar. These sound really familiar. In fact, if we actually read them backwards, 1, 1, 1, 1, 3, 1, you're not very impressed yet, 1, 7, 6, 1. We saw those numbers before. Do you remember? What are they? Those numbers were the Stirling numbers of the second kind. And it turns out that that's not a coincidence. There are the Stirling number of the second kind and n minus k ways to place k non-attacking rooks on this n triangle. Now, if you're trying to remember, wait, what was the Stirling numbers of the second kind? Well, that says you take the numbers 1 through n. You really can think of it as just n distinct objects. So for us, it's very convenient to say, okay, the numbers 1 through n. And now what you want to do is say, I want to break them up into a certain number of groups. And we call these sets. But you can just think about it grouping. So I want to break a set of n objects into n minus k groups. How many ways is that possible? That's what the Stirling number of the second kind counts. So why is this so amazing? Well, it's because it doesn't feel like things should be connected. When you see this, you're like, wow, wait a second. How in the world does Stirling numbers of the second kind have anything to do with placing rooks on this board? And that's why it's such a beautiful idea. And I love math, which is beautiful. It makes me happy. And I hope it makes you happy too when you are doing beautiful mathematics. So how does it work? Now, you can argue in lots of different ways, but I like to do it by saying, hey, I can show you a way to go back and forth between objects. So, in other words, this is what they might call a bijective proof, which is just saying, for every object here, you have a similar thing over here. And there's a rule that takes you from one to the other. So what are the 2 things we're talking about? We're talking about ways to put rooks, and we're talking about ways to break things into smaller groups. Now, the rule is very simplified. Probably it's a little bit oversimplified, but this is sort of the rule in the back of your mind when we're talking about this. So it says, look, if a rook is in a row with label I and a column with label J, then I and J should be in the same group. And you should do that for every single rook. So you say, okay, essentially what was going on here is you're saying that the rook should identify what should go together. So what do we mean by that? So for instance here, if we put a rook in, it says a row has a 3, column has a 7, 3 and 7 should be together in the same group. That's what we mean by the rule. All right, so here's where it can get fun. And all right, let's try some very simple examples. And I think it's best seen by doing a few examples. So I want to show you how you go from rook placements to some sets, and then we can also do an example where, oh, okay, here's a set. How do you get back to rook placement? Okay, so let's put a couple rooks down. Well, not too many. we don't want to be too greedy at the start. Okay, there we go. We'll just do those 3 rooks. Right, that should be enough. Now, here's how you can find your sets. What you do is you just start at 1 and you go until either you hit a rook or you exit. Now, if you exit, then you're done. So here we're starting at 1. So we're starting at 1 and we exit. All right, so that says we're done with that group. Now we go to the next one. Okay, well, we haven't seen 2 yet, so we'll start at 2. So we see 2, come along, up. If you hit a rook, go up, and it says, look, 2 should be with 3. Okay, so we'll put 3 in. Now we start going across. Okay, 3, whoop, we see something. Okay, so 3 should be with 7. All right, 7. All right, now starting at 7, and we exit. So we're done. All right, so 1, 2, 3, 7. All right, what haven't we seen yet? Well, the smallest thing we haven't seen is a 4. Okay, so that'll be our next one. 4, nope, doesn't see anything. We just exit. How about the next number, 5? We exit. Okay, great. And so, how about the next one? 6, so we'll start with 6. And we go across. Ah, we hit a rook. And where does that say? 6 and 8 need to be together. And of course, 8, we're going to exit. And there we go. So this rook placement gets us 1, 2, 3, 7, 4, 5, and 6, 8. Now you'll notice here, because of that sort of rule in the background, every time we place a rook down, we're saying, oh, 2 things should go together. And so if you think about it, we say, hey, it's almost like if you start by doing like a big puzzle, right? And you ask yourself, suppose you have a 1,000-piece puzzle, and you want to build it. And every move is putting something together. Well, what's the minimum number of moves that you need? Well, the answer is 999, because every time you do something, you're putting 2 things together. So every time you put a rook down, it's like, oh, I'm putting 2 things together, which means I'm taking the number of sets down by 1. So if there's no rooks, then everything exits out, which means that if we have this n board, we'll have n sets. Every time I put a rook down, oh, it's really putting 2 sets together. And so that's what's happening here. You're seeing this sort of action coming into play. All right, well, let's do this a few more times, because one of the things is the more that you do it, the more that you're convinced it must be true. And, well, you already know why it should be true. But still, it's always nice to be more convinced, right? The more you know, the more you know. And with that, the further you go. There we go. There's a bunch of rooks. No 2 are in the same row. No 2 are in the same column. Okay, well, let's try this one. Okay, so again, starting at the bottom, we start with 1. Well, does anything go with 1? So we go across, up. We see a rook, we go up. 6 should go with 1. Okay, does anything else go with that? We'll start with 6, see a rook, boom, up to 7. Okay, all right, and from 7, shoop, we exit. So 1, 6, 7, okay. All right, how about starting at 2? 2, and what do we see? Well, we see a rook, and what does that say? Well, we should have 2 and 4 go together. Okay, 4. All right, how about from 4? Well, 4, we see a rook right away. It says 5 should also be there. All right, great. How about from 5? Zoop, exit. Done. All right, what's next? Well, next is 3. We haven't seen 3 yet. So we always start with the smallest number we haven't seen yet when we're writing these down. Okay, well, how about 3? Well, we start at 3, and that goes all the way up. There's a rook, up to 8. And then from 8, well, not a lot of options. You have to exit. And so 3, 8. Okay, have we seen everything? Well, 1, 2, 3, 4, 5, 6, 7, 8. Good. Everything's been accounted for. And you'll notice we can check how many rooks we have. We have 1, 2, 3, 4, 5. And how many sets do we have? We have 3. So the number of rooks plus the number of sets should add up to what n is, which is, in this case is 8. Okay, well, so that's not so bad. So you can actually think about just sort of zigzagging. Every time you see a rook, go up and then start moving to the right again. Up to the right, up to the right. Okay, now, what if we were going to do the opposite thing, which is saying, okay, let's not start with a rook placement. Let's start with sets. Can we find a way to break up can we get from a set of sets to the rooks? And what's the procedure? Well, okay, so let's write down some breakup. Okay, so suppose we want, well, we'll put 1, 3, and 6 will go together. And what else do we have? Well, we haven't accounted for 2 yet. We'll have 2 and 5 and 8. And, well, we can have 4. All right, 4 can be by itself, and 7 can be by itself. So suppose, for instance, we wanted that. How can we put the rooks down that gives us this particular configuration? And it's actually very simple. Here's the rule. Okay, whenever we have the elements, we're going to put them in order here. We say, look, 1 and 3. So these are going to go in increasing order. So that says what? Well, that says I need to have something where I'm going to have a turn from 1 to 3. So we should place a rook right there. So we go from 1 to 3. Now, how about this one? 3, 6. Okay, so I need to have a turn from 3 up to 6. So in other words, look for the 3 and the 6 intersect, and you put a rook. Okay, we have some more. 2, 5. Okay, so wherever I see 2 going up to 5, I'm going to put a rook down. Great. And 5, 8. So 5 up to 8 means put down a rook. And 4 and 7, look, there's no pairs. So we don't need to put any rooks down. And they'll take care of themselves. And now, if you do the same procedure, follow it through, you'll see 1 goes to 3, 3 goes to 6, 6 goes out, 1, 3, 6. 2 goes to 5, 5 goes to 8, we're out, 2, 5, 8. Nothing with 4, nothing with 7. And it's done. I love this. This is such a cool thing, and it's really beautiful. I love when things are unexpected. But at the same time, when you see it, you say, oh, there's this nice natural rule. And it's one of the things, it makes me happy that I get to see it. And I think some people like to say mathematicians get to see some really beautiful things. And I agree with that. I think math is a beautiful subject. And I love that I get to be involved with it. And I get to do it. All right. Well, okay. This was a fun little aside. We need to get back into looking at our rook placements on our square boards. And we're going to talk about next saying, hey, what happens if we have our nice square boards and we want to count how many ways to place rooks below the diagonal? We want to look at those numbers a little bit more closely because they're going to be important. All right, see you soon.